Welcome back. We continue our journey through differentiability by writing down, well, basically some stuff you probably learned in Calc 1, but it's good for us to write down all these things again, most importantly so that we see the hypotheses, right? As is usual in this course, yes, the conclusions are important, but our real interest is a lot of times in these hypotheses. So let's start. We're going to write down two theorems in this video. So the first one is called the Algebraic Differentiability Theorem. So this should remind you of a lot of our algebraic theorems that we've had during this course. All right, and they all basically start the same way. We are going to have some hypotheses about some functions, say f and g, and then there's going to be some conclusions that'll have to do with multiplying the function by a constant or adding the functions, etc. So let's see here. So first, we're going to start with two functions, f and g, with a common domain D. And I'm going to choose some point A. And since we're dealing with differentiability, I'm going to assume that D contains an A coin, i.e. A is an interior point of D. And then we're going to take C to be some constant in the real numbers. This will be something we can multiply by. Okay, so that's our notation setup. But now, if we're going to talk about differentiability of things like f plus g or f times g, etc., we need to make some assumptions about f and g themselves. Namely, they should be differentiable at some point. In this case, we're talking about the point A. So we're going to assume, right? So if f and g are differentiable at A with derivatives, and we'll probably stop writing this part soon, with derivatives f prime of A and g prime of A. Okay, so this is just the name we give to the derivative at those points. Okay, of course, this is respectively. Then the following hold. Okay, so number one, that's right, you guessed it, homogeneity. All right, so if I multiply my function f by some constant c, I get a new function, and this function is still differentiable. All right, I'll abbreviate differentiability with diff at A. And what is the derivative? So the derivative I get, well, I take the derivative just for f at A, and then I take this number, right? So this is just some real number, and I multiply it by c. Okay, so that's how we handle our business when, okay, for example, right, if I take the derivative of 2x cubed plus 6x, we know that derivative is 6x squared plus 6. And what if I was going to do 3 times this function? So 3 times 2x cubed plus 6x. And what this theorem tells me is that instead of distributing the 3 and then taking the derivative, I can instead take the derivative of 2x cubed plus 6x and then multiply by 3. So I'd end up with 3 times 6x squared plus 6. And you can check that it didn't matter if I did distribute this, right? Oh, I'd have 6x cubed. When I take the derivative, I'd end up with 18x squared. Hey, that's what I'm going to get there too. Okay, second piece. If I add the two functions f and g, this is still a differentiable function, at least at the point A. And the derivative is given just by taking the individual derivatives and adding them together. So I can differentiate term by term. Okay, now when we did the algebraic continuity theorem or the algebraic limit theorem, the next thing is I would say, oh, but you know what? It doesn't matter if you have a plus or a times, right? You could do either one of them. And here I'm actually going to break it up into two pieces. Not because the first part is different. In fact, that's exactly the same. The product of f and g is differentiable at A. However, when I get to with derivative here, I cannot just write f prime of A times g prime of A. Okay? Instead, we have to use the so-called product rule. So this would be f prime of A, g of A, plus f of a g prime of a. Okay, so this you should know. And if you do not know, you need to go learn it. This is a necessary part of this course to know the product rule. Okay, unsurprisingly, then you also need to know the quotient rule. So that's what's coming here next. So the quotient rule says, well, what if we have f divided by g? And unsurprisingly, this will also be differentiable at a. And because we know about the quotient rule, we know that the derivative is not just f of a over g of a. Instead, we get f prime of a g of a minus f of a g prime of a divided by g of a, and then we take that quantity there and square it. Okay, so that's a little bit of a crazy one. Of course, as with all of the quotients, we have to add in the little proviso that the denominator, right, isn't zero. So provided g of a does not equal 0. Okay, obviously this doesn't work so well if g is equal to 0. Okay, so that is going to be our algebraic differentiability theorem. I would love to put one more thing into this, namely the chain rule, but the hypotheses of the chain rule are just different enough that it's worthwhile that we start over with another theorem. So, new theorem, the chain rule. All right, so the difference here, right, I don't want to have f and g have a common domain typically. Instead, I need to have two functions where one of them, its output is in the input of the next function. So here I'm going to have a function f that can go from, say, d to r. But now my g, well, that could go from some e to r, but it needs to be the case that the image of f is contained in e, because I want to compose these. Okay, so I want to do f composed with g. Okay, and this only makes sense if all of the outputs of f are actually in the domain of g. Okay, so that's what I'm saying here. The outputs of f are in the domain of g. Okay, now let's see, what do we need? Well, we probably want some a in the interior of d. That way we can differentiate. And we're going to assume that f is differentiable at a. Okay, so I can take the derivative at a. G, this is where people make a lot of mistakes for some reason. They say, oh, well, I also want to assume g is differentiable at a. But that doesn't typically make any sense because a is in d, and we don't know anything about d being in e. We only know that the image of f is in e. So we're not going to assume that g is differentiable at a. Instead, we're going to assume it's differentiable at f of a, which is fine because that's how we get anything into g anyway. We put a into f, and now we have f of a, and we put f of a into g. All right, so we have this. The conclusion, okay, so this is all the hypotheses. The conclusion is that the composition, let's get in the right direction, the composition G composed F is also differentiable at A with derivative. Okay, so how does the chain rule work? You take the derivative of G at F of A, and then you have to multiply by the derivative of F at A. Okay, so G prime of F of A times F prime of A. Okay, so there's the chain rule. So we're not going to prove either of these theorems in this video. We're going to save that for the next iteration of the course. These are things you absolutely need to know about calculus. So yeah, get to making sure you know not just the conclusions, but the hypotheses. All right, we'll see you next time when we do things like Fermat's theorem, Darboux theorem, Rawls theorem, mean value theorem. Okay, maybe that's too much for one video, but we'll jump into those in the next couple. We'll see you there.